Hey, we'll go ahead and get started here. Hopefully, others will show up in the next few minutes. Uh, Welcome back. And today we will be continuing through our sweep of discussion regarding uncertainty in agent-based modeling. And we've talked about a set of methods for exploring such uncertainty, from exploring implications of stochastic variability on model outcomes and trade-offs between interventions or policies. We've spoken about systematic exploration with parameter variation experiments, both parameter sweeps and Monte Carlo-based experiments, and understanding how those impact model outcomes or trade-off between policies. I gave some nod to how that intersects with, but also broadly highlighting the need for structural sensitivity analyses, understanding how our assumptions of model structure impact model findings and outcomes, scenario-based trade-offs. And I had noted in making those comments that an important additional technique of relevance here and of extraordinarily widespread application is what goes by the name of calibration. It's sometimes also called automated parameter estimation. And fundamentally here we are estimating parameters by matching model outcomes against data. Now, calibration is a sizable topic in and of itself. The topic of calibration has many technical sides to it, and we'll talk about different dimensions of such sides. The optimization algorithm one uses, how one specifies the discrepancy or goodness of fit of model results to empirical data. What sort of empirical data can you use as part of calibration? The degree to which you're trying to do point matching versus characterizing summary statistics. All of these have relevance. Beyond those, there's some issues involving probabilistic formulations of matches. And this gets into issues with things like approximate Bayesian computation and formulating calibration in a manner that's more probabilistic and accounts for uncertainty in matches. A separate issue on the calibration side concerns how the relationship between calibration on the one hand and parameter variation experiments on the other. The degree to which you perform parameter variation experiments to identify sensitivity of model results to certain parameters, and then perform calibration on those parameters, an oft-used strategy. We calibrate parameters to which the model is highly sensitive in the outcomes of interest. But there's an argument to be made that the reverse order confers value as well. You calibrate, and then based around the point of in parameter space where you have estimated those parameters, you sense sensitivity there and assess model sensitivity in light of those parameterized values, reflecting the fact that with different assumptions about parameters, we may have quite different sensitivity, especially in a nonlinear model. So there's a set of issues there. And in general, calibration, you could, if had we time, we could probably spend readily 3, possibly 4 lectures speaking about different aspects of it in an agent-based context. As it is, I'm going to try to confine my comments mostly to this lecture and to tomorrow's lab session, where we'll be exploring some hands-on calibration, some hands-on challenges. However, some of these ideas that we explore here will come into our discussions of statistical filtering and potentially, as time allows, approximate Bayesian computation. Okay, so with that motivation and those that broader context in mind, I'd like to switch now to talk about the topic of calibration. So I'm going to be situating calibration within this broader context of systems data science methods, which involve filtering techniques, estimating model state, particularly as data comes in from the world, in the context of a stochastic model, a model where even if you have parameter estimates, you don't know exactly what it will do next because there's stochastics. There's happenstance. You can't be expected to predict its exact outcome, too uncertain. You might anticipate broad regularities of its outcome, but in terms of what exactly it does, you need to reground yourself periodically in observations as to what's really happened. It's a bit like the weather, right? We may have outstandingly accurate weather models, but it would be a fit of madness, particularly on a snowy day here in Saskatchewan like this one, to rely on one of those models from January 1st to predict the weather for tomorrow. It would be madness. The model might be extraordinarily well-grounded, scientifically rich and accurate model, but we would never think of relying on its estimate for the weather tomorrow based on the model's initialization as of January 1st. We would need to update it as to whether how certain uncertainties played out, how that cold front moved, how the actual measured humidity in the air, the amount of snow that actually came down on snowy Saskatoon on the afternoon of March 25th, 2026. And using that, we could have a much better estimate of what will happen tomorrow, because there are some things that are not in the ken of exact prediction. They demand recognizing there's a certain range of variability we can't precisely predict, and that our models are fallible. And we're much better off just regrounding our model as to what actually happened so we can predict much forward going forward. That's a matter of filtering. And that is a technique that holds relevance and works alongside calibration, where we're seeking to estimate parameters. And some techniques, such as particle Markov chain Monte Carlo techniques, that are the bread and butter of some of our work in our lab, lie at the intersection here. They estimate parameters, but they also estimate the state of the underlying system. Kalman filter can be used for that if you characterize parameters in a stochastically evolving way. But here we're talking about techniques to estimate parameter values. I will note that I've taught several boot camps and a fields course on this broad picture, exploring these various techniques as well as others, including things like approximate patient computation. And there are many videos of me, perhaps too many, holding forth on each of these techniques that you will find. Let's talk about calibration. We're gonna speak about this process. The observation here is when we have a model, such as those we've built, such as those with which we've worked, there are frequently parameters in that model where we lack really effective data sources for them. Perhaps we are aware of some estimates, but they're estimates from outside our jurisdiction. Perhaps they're estimates from certain subgroups in the population. Perhaps they are estimates that are somewhat old, somewhat outdated. Perhaps they're estimates that are rough and tainted by the fact that the questions being asked for people included meant that they were answering in a way that wasn't exactly what we wanted. Or perhaps there's known confabulation by individuals in answering these questions. Whatever the reason, and in other cases, we have parameters about the underlying, the latent structure, the underlying drivers for dynamics where we don't have direct observables corresponding to them. We have no way of directly measuring, perhaps, or no feasible way, tractable way, realistic way of measuring these factors. Perhaps factors that are simply unrealistic for ethical reasons, for reasons of expense, of logistics, to realistically measure. Perhaps factors involving human behavior, human decision-making, matters involving factors such as stress or aspects of belief or trust that collection is challenging. But we have a model often that were we to plug in assumptions about those parameters would exhibit emergent behavior. It would result, the logical consequence of those assumptions about those parameters together with model structure would yield certain behavior by the model. We've seen that again and again. The model runs over time and outcomes, successive outcomes play out over time from that. Those are the logical consequences of our assumptions about those parameters. So even if we don't have specific estimates for those parameters on their own, individually, we do seek assumptions about those parameters that yield outcomes from the model that are broadly plausible in light of what we see in the world. Because often, not always, but often, very often, there are observations that relate in the world to emergent outcomes. Things like the number of people who are reported as having COVID over, on a day-by-day basis over time that don't relate to any one parameter in isolation. They don't tell us immediately what the contact rate is. They don't tell us what the mean recovery time is. They don't tell us the probability of infection given a certain type of contact. In and of themselves, the number of people getting infected on a per day basis. But they certainly are influenced by our assumptions there. And if we have a model which has outcomes involving number of people getting sick on a per day basis, we hold it to offer some fidelity to offer some comparability to offer outcomes that can be hold up plausibly in light of what we actually observe from the world. So here we're in calibration, we are taking parameter values that we don't know as well, or we don't have firm values, and we try to adjust our assumptions about them such that the model's outcomes best match observed data from the world. Of course, if we have data from the world involving experiments, measuring people's contact patterns, their duration, the length of, the time between those contacts. If we have data from the Avicenna platform that we built and have used for, dozens of contact studies over the years, if we have data from that, of course, we can put it into the model. But for many parameters, we don't have data. We're building models of latent systems. And where we don't have data, we can still seek to test our assumptions about parameters against the crucible of empirical data by comparing model outcomes, emergent behavior, endogenous behavior against what we see from the world. And typically, we'll hold the model to account to match many observed time series or many observed data points that we may have from the world. So we're trying to ask, what must these less well-known parameters be, or what are plausible values of these parameters in order to explain this data we see from the world? That's given an assumption of model structure. Given we assume a certain model structure, what must be the values of these parameters such that I can best account from this data from the world? Importantly, in an emphasis to which I'll return at later points in this talk and on Thursday and tomorrow, we sometimes learn that our model just doesn't cut it, that our model can't explain patterns from the world. It just does not add up, that the model matches certain things but is woefully unable to account for others. That is not a speed bump. That is not a failure of the model. It is a success of learning. That we learn that our best understanding of how the system works just doesn't, it can't explain certain phenomena. It can't account for what we see from the world. That is debugging our thinking about the world. That is moving our understanding forward. That is a discovery we wouldn't have had we not built this model. We wouldn't have realized our cherished understanding of the world as captured in the model, our best guess as to how the world works, just doesn't add up. It took a model to do that because it is with simulation that we simulate the logical consequences of the model and find that when they try to match observed data, they are found wanting. They can't match that data. And that's a great opportunity for learning. Okay, so calibration is about tuning parameters to best match data from the world, but it also is about testing our model assumptions, our structural assumptions, as to whether they can indeed rigorously account for many observations from the world at once about endogenous behavior. So calibration can be seen as helping speed us towards a dynamic hypothesis that explains the observed data. And sometimes we find we have to go re-examine our hypothesis more deeply. Sometimes we find it's a matter of tuning our assumptions about parameter values. Now, calibration can also be seen as a technique to leverage information regarding emergent behavior that we have at our disposal, but can't be used to directly parameterize our model. There are many times where we have data from the world that relates not to any one parameter, and we wish to make use of the data, and often calibration is a very good way to do that. Okay, so I've waved my hands about calibration. The nitty-gritty of it is that calibration uses a global optimization algorithm to try to adjust unknown parameters to automatically match data. So the model results, model outcomes, model emergent behavior, model endogenous behavior. I'm describing it with different words, but pointing at the same thing, best matches this observed data. And the point is it's using global optimization. It's trying to find the best fit, tuning our assumptions about parameters to locate the best assumptions about those parameters. And in order to do this, we're going to need to specify several pieces of information. One of the key ones we'll see is an objective function, which relates to how good a fit the model is allowing, or if we take the negative of that, how big the discrepancy is between what the model produces and what we observe in the world. And the optimization algorithm runs the model many, many times, often thousands or more, tuning parameter values, adjusting parameter values to identify the particular assumption about parameter values that yields the best or the lowest discrepancy match to that data from the world. Okay, so what information do we need to specify for calibration? Well, we'll be going over that right now at a high level. Tomorrow, from this seat, I will be walking you through some hands-on exploration of calibration with a model. That is a process that can be undertaken manually to some good effect, but as we'll see tomorrow, can also be supported computationally in a powerful way. Well, what information is needed to undertake that? Regardless of platform, this is not a platform-specific issue. What's needed in order to calibrate a model? What type of information? Well, one thing is a choice of what data to match. What is the data we're seeking to match from the world? Secondly, what parameters we wish to vary. I mean, which parameters we're trying to estimate. For which parameters do we not have requisite data we're willing to stand by, and where instead we want to try to estimate those parameters such that the model behavior best matches this data from the world. So we have to know what parameters we want to verify and over what range we want to verify them. Maybe we have estimates for these parameters from several studies, or maybe from different jurisdictions or different pedigrees of estimates from past studies. Maybe from different meta-analyses in the best case, maybe from different clinical trials, maybe from different countries that give us some range, perhaps. And we want to assume a value for the parameter that's within that plausible range somewhere. So often we identify which parameters to vary and over what range to vary each of them. And then we're going to need to specify an objective function. And the objective function, or which can be phrased as a discrepancy function or error function, how bad a match is, or it can be flipped around, take the negative sign, and be a payoff function, a goodness of fit that you want to maximize. Really, it's a matter, do you want to minimize discrepancy between what the model produces and what you observe from the world so that you try to get them as close as possible, you minimize the discrepancy, or do you want to try to maximize the goodness of fit there? You can phrase it either way, but the point is you have an objective function you want to optimize, maximize, minimize, pick how you want to frame it. And this objective function will reflect the data. it will reflect the model output corresponding to the data that needs to be compared with the data, and some sort of way of weighting to say, like, how much do you care about a mismatch here versus a mismatch there? Maybe some things that are observed from the world, you don't trust the data that much to which you're trying to match it. Some things the world you trust a lot more. Maybe they're more core to the project. So you give them a higher weight. You care about them more. You try to match them with greater fidelity. We'll come back to this point in a form in just a moment. And then finally, and again, this is a matter of sort of technical substance, technical richness, and a topic on which one could spend many lectures. One specifies a desired optimization algorithm, commonly a global optimization algorithm, that will help you locate the particular set of parameter assumptions, one value for each parameter, such that the model outputs with that assumption best matches all this data you have from the world. Okay, so here, if I may, and I'm getting these little Zoom widgets, which seem to get in the way of things. Here we have a depiction of parameter space. So imagine that beta, tau, and mu, or to go alphabetically, beta, mu, and tau, are each parameters. And we have different possible values for the parameters, right? A particular value for beta will be like a plane here for different values of mu and tau. But a particular value for beta, particular value for mu at the same time, and a particular value for tau is a complete parameter vector. It's an assignment of a particular value to each of these parameters, right? That'll be a point in this cube. You people get it? A point in this cube will have a specific value beta, that's its direction that way, right? Particular value mu, right? Going this way, and a particular value of tau. That'll be its coordinates, right? And what we're doing is we are trying to find the particular values of each of them, trying to find the point in this cube such that for that assignment of values to parameters, the model results, the result of running the model on that assignment of values to those parameters is as close to the observed data as possible. Gives outcomes, give behavior over time, or gives summary measures that match what we see from the world as closely as possible, right? And I hope you'll recognize the statement, what parameters to vary is like beta, mu, and tau. The range over which to vary them would be this range here for beta, this range here for mu, this range here for tau. And this objective function is going to relate to how we judge how good a fit there is, or how big a discrepancy there is for a particular point in this cube, a particular assignment of values for each of beta, mu, and tau. That's going to yield certain model behavior, and we have to judge how close is that, right? Or how far is that? Again, flip, your choice of how you measure it, from the observed data from the world, the corresponding data from the world. So if you run the model and we get this many people reported as being infected by COVID in the past day, and we try to match that from the world, and the model result is 351, and the data from the world says 401, it's a difference of 50. And we say, is that good? Is that bad? Well, that's what our discrepancy metric, our error function, needs, measures, right? Okay. So we have to have some way of measuring like goodness of fit, or badness of, its discrepancy, how big the discrepancy is, right? I will prefer here to talk about a discrepancy metric, a metric of like how far off the model is, how bad is the model's match, with the best match being zero discrepancy, exactly matching. And we'll talk about why that's often an unrealistic bar, why that's too high a bar, too unrealistic a bar in just a few minutes. But zero discrepancy would mean exact match. Do people appreciate that? Okay, so I want to talk about a desirable discrepancy. Like, okay, if we're trying to characterize how much discrepancy there is between the model result on the one hand for a number of people infected for a given day compared to that from the world, like what is the property of this way of quantifying it that we want? If we want to do that for multiple data points, for successive days, and we want to do it for a number of deaths of people with COVID, and we want to do it with number of hospital admissions, and we care about all of them, we have a model that includes each of those, and we want to compare each of those to the world and characterize accordingly. What is the characteristic of this discrepancy function? Well, several of them that we want. And I'm going to put forward a set of desiderata. We would like it to be dimensionless. Why? Because look, another term for this is of unit dimension. We want to be able to add a discrepancy for being off in terms of number of people being diagnosed with COVID. We want to have a discrepancy for that and add it to a discrepancy for being off with respect to new admissions to the hospital for COVID, and add it to some discrepancy for the number of deaths per day from COVID. And to add them together, they cannot be of different dimension. They have to be of the same dimension. You can't add dollars and people together. You can't add new cases per day on the one hand to number of deaths on the other. They're incommensurate metrics. So you need to express them in a dimensionless form that can be added. I'm not going to go into that more. There's whole lectures I could give on that are important and valuable, and you will find good approximations of them from me when I wore younger man's shoes, and sometimes not so younger, on the web. So dimensionless quantity is a desirable feature because you want to be able to add discrepancies. There's other criteria there as well, reasons we want dimensionless, but I'll just leave it there for now. We want it to be weighted. Look, we have different pedigrees of data. Some data we trust more than others. Some data may have more error associated with it. Some data are more core to our model goals. Maybe our model centrally has to do with people being hospitalized for and risks of death from COVID, but is only tangentially related to contact tracing data. And so we have contact traces, data, number of people located through contact tracing. Maybe that, or maybe even the number being diagnosed, are of more peripheral interest. We want to match them. We'd like to be able to match them, but it's not as core. So we weight them less. And there's actually arguments to be made, which I've explored in past work, that data which has been estimated with a smaller sample size might be associated with the lower weight because there's statistical error associated with it. There's more reason to be suspect about a given data point, and one might weight this by some measure of 1 over the variance or what have you, a given estimate. this should be an analytic function. We should be able to differentiate functions one or more time, ideally, to be able to speed up the optimization process. This is not a strict requirement, but if people know about optimization, one thing that's quite favorable in optimization can allow you to proceed more quickly and therefore explore more of the space and therefore arrive at a better, more reliable estimate, is that if you can understand how the space is shaped, like what direction I could change these parameters to help reduce the discrepancy at any one time, that can speed it up. This should be concave. Two small discrepancies, one might argue, of size A should be considered more desirable than having one big discrepancy of size 2A for one criteria and none for the other. We don't want to rob Peter to pay Paul. And generally speaking, if we can have a smaller discrepancy for each of two things and keep it close, that's better than having a big one for one and none at all for the other. This is somewhat arguable. It's a common sense notion that you'd like to kind of distribute the mismatch among the several things rather than having one thing that's privileged over others. It does have to be considered in light of the weighting. It should be symmetric. Being off by a factor of 2 should have the same weight, regardless whether we're 2 times off or 1/2 the actual value. That too is somewhat debatable. You could say, really, I want it to be absolute, not relative, not a matter of, is it 2 times the value, but is it some amount more than the value? But in many cases, we might like it to be symmetric in this way. Non-negative, certainly you shouldn't have a really good, like, it shouldn't be that one discrepancy should cancel out others, or one lack of discrepancy should cancel out others. We shouldn't consider one discrepancy to kind of mean others don't matter. So I say non-negative, and it should be finite. We shouldn't have infinite mismatches. So I give a criteria here, which we've used to good effects. I won't go into its mathematical properties in detail, except to say that it matches all of these. So we have a weight here up front. We have a difference between a historical number and a corresponding model quantity divided by the average between those two. I would note that this is 0. If H and M are non-negative quantities, right, or never go negative, this is 0 only if H and M are both 0, in which case H minus M is also 0. So the denominator is only very small if the numerator is as well, I will say. It is the ratio of these two. Both of these are of the same dimension. We're comparing a model quantity against its empirical analog. So these are of the same dimension. These are of the same dimension. And the numerator and denominator are of the same dimension. Therefore, that cancels. Therefore, this is dimensionless or of unit dimension. And it's squared, so it's concave. It's concave. Okay. So we, in terms of this, we prefer 2 small discrepancies to 1 twice its size. Okay. So considerations for weighting. Well, I spoke about this a little bit ago. I would just say, look, if no data exists, the weight is conceptually 0. We don't weight it. We have no basis on which to weight it. If we have greater uncertainty in measuring in empirical data, in empirical datum, then the weight generally be lower. And if we care more about a match, if it's more central to model goals, again, we can weight that more highly. So if the model is really dealing with hospital care for those with those who are diagnosed with COVID, maybe we give higher weights involving terms for admissions and mortality, and if we have data, discharges. But maybe we weight those higher than number of new cases or number of individuals found via contact tracing or what have you. So maybe we have model components which relate to those other things, but we don't weight them as strongly. There are many cases where we have data from the world. So I'll just note the form of this. We'll talk more about some forms tomorrow. We'll see an additional form. A few extra considerations here. One thing is there are a fair number of cases where we have data from the world that exhibits stochastics, that exhibits uncertainty. And sometimes it's actually a motivator for use of agent-based modeling that it can characterize those stochastics, that uncertainty. There are times where I have used agent-based modeling because of the stochastics involved in it to show that certain patterns we see from the world are completely consistent. They are consistent with a dynamic hypothesis captured in the model, simply because of stochastics. That they may look like they fly in the face of the theory, but no, they actually result from the theory because when you consider stochastics, it can be expected to yield these symptoms. And therefore, they are by no means undercut the viability of the theory. I could show that with the NABM because it exhibits stochastics and its outcome that can be compared with variability seen in the world and show that it's completely consistent. But data from the world to which we wish the model to hold true, to which we wish the model to maintain fidelity, is often marked by happenstance. Each of these small twists and turns, these crenulations that we see exhibited here historically so well for pertussis here, for in England and separately in Wales, for example, they exhibit certain regularities, certain orderliness to them that is undeniable. They have peaks and troughs. There's some anti-correlation where a peak at one time means there's unlikely to be another outbreak that soon. We could say in this forum that it's because of depletion of susceptibles, but the point is, while there is orderliness here, this exhibits some real orderliness to it, these patterns that are undeniable, but it also exhibits stochastics. The particular peak, the particular size of each one of these peaks, the exact timing of these kind of minor peaks, whether there was an outbreak in this year or the previous year or the next year, the exact timing between these, whether it's 6 years or 7 years or what have you, it has some circumstantial components, has some happenstance to it. You could argue that these peaks could have occurred all 1 year later than what's shown here. Imagine shifting them all by 1 year, or indeed shifting each and every one of them by 3 years. And that would not in any way particularly fly in the face of the theory. the basic dynamic hypothesis involved. Because it's not time dependent. And if I were to utter the term, something about the stationarity of the process, Mehdi would understand, my meaning here. This is chickenpox in Saskatchewan. And again, I would argue that the exact timing of each of these peaks, whether it occurred all of them occurred at these times or 2 years later, each in each succession, is probably not strictly dictated by some underlying physical limitations. There's a fair bit of happenstance. What is not happenstance is the underlying dynamics associated with the ebb and flow, the waxing and waning that we see here for measles and mumps within our fair and snowy province. Okay, so I want to talk about this with these timings. So when we are talking about a stochastic model, which we typically are in the province of ABM, the non-snowy province in that case, we're moving beyond point matches often. We could try to match an ABM to each of these peaks, right? Historically, we could try to match it, but we'd be on somewhat of a fool's errand. It would be as if we had a hydrological model involving the flow of rivers, and we tried to match each and every wave out in yonder river, the mighty South Saskatchewan flowing through town. If we tried to match the sort of rise and fall of every wave, it would be a fool's errand, right? It would signify nothing of significance that we can match the exact timing of each and every wave against the piers of the University Bridge. Instead, we want to capture the regularities. We want to capture here the waxing and waning, and not necessarily the exact timing, the precise month of an outbreak, which arguably lies outside the purview, the remit of realistic science, any more so than matching the exact timing of each wave within our mighty and scenic river. So I would argue that ABM calibration needs to be undertaken with the recognition that as a stochastic model, it can rarely allow for closed point matches to noisy empirical data. Matching empirical time series at data points is not an indication of a poor quality ABM. Like matching, failure to match each and every one of these peaks at the exact time it occurs should not be viewed as counting against the validity of a given ABM, any more so than a hydrological model should be judged wanting and judged insufficient just because it cannot characterize the exact timing that a wave will splash against Pier 3 of the University Bridge. Instead, we seek to match and assess ABM matches against some sort of summary measures that capture these regularities, capture this orderliness, capture the essential statistical properties of it, the underlying regularities of it, without committing to the infeasibility of matching the exact timing of each and every match, of each and every specific outbreak. And that, dear viewers, is indeed the goal, in my view, of much, not all, but much of calibration with ABMs. So I've given examples from some of our work. This is substantively our work with Wade McDonald, Karsten Hempel, and really Alex Doroshenko as the real drivers here. So here, you notice we're matching against historic data against pertussis. It's not that we didn't have time series for pertussis. Oh, we certainly did. But we weren't embarking on the fool's errand of matching each and every month or year worth of data. Instead, what we're matching is, cumulative density of yearly incidents. So this is a cumulative density function representing on a per year basis how big was the outbreak this year. It's a cumulative density function rather than a probability density function, reflecting what fraction of outbreaks were less than a certain number of people per year who got sick, reported as being sick from pertussis, right? So here, for the jurisdiction we were looking at, this might be something like 30, and something like 90% of yearly ones had fewer than 30 people infected. Here's age distribution that we were matching based on empirical data, the distribution of ages in those across different outbreaks. Here's autocorrelation. So some may here be familiar with the notion of an autocorrelation function, characterizing to what degree a data point at a given point exhibits correlation against the data point the next time point out. Maybe it's the next month out or next year out, against the next one yet, against the next one yet, and against the next one yet. And generally, we will find here negative autocorrelation for the first. A big outbreak here leads to fewer in successive months, or successive years, rather. But then it will be U-shaped, because after a certain number of years, big outbreak now may mean more likely in, say, 7 years, because it bounces back. There's going to be a rebuilding of the susceptibles. And so we look for the model to match this. Blue is empirical data. These bars here are from the model successive realizations, the model, running it again and again. This is relative risk involving timing of vaccine dose, here's vaccine coverage viewed as endogenous. We also, from this model, we're matching model-generated patterns of contact against corresponding empirical data on contact patterns over time. And you'll notice the age of the contactors on this x-axis, the age of contacted is here, and you'll notice some intergenerational features here. So children in a certain age tend to have parents of a certain age associated with them. So if you have a parent, they may, a person of a certain age, say in their 30s or 40s, they may spend a fair bit of time around younger individuals who grow successively larger, right? In some data, you can see grandparent effects, etc. So, with all of this, what types of things might we examine coming out of a model that we wish to sort of summarize? Well, I'm not dealing with the summary part here, but what things? Well, we might want to have cumulative counts of some sort, like the number of people getting sick over time, the number of people buying a product for, consumer model, what have you. Incidence rate, could be cumulative, over time. Individual level state, summaries of, or something about individual level state or individual history, the count of times they experienced something or undertook it, how long they've been homeless, right? The time between individual level events, between them becoming homeless or between them, purchasing a property or what have you. And there might be per a session we had probably a good 4 or 5 times ago now, aspects of the reconstructed state space like that has some features in it that we can compute from empirical data, and we can ask for the model what's implied for this and see if they match, because for the empirical data, we know that certain reconstructions give us a hint of give us the characteristics of the process that drove that historic data. And we could see if the model's outcomes indeed match that. Now, look, okay, so if we measure some things here, and these are just some ideas, they're awfully generic, and, for your models, there might be different ones. What sort of summary measures might we give for these? Well, again, some simple notions, simple ideas. Mean, modes, medians, right? We can characterize here the mean incidence and try to measure that, right? That's what we do here, empirical data, what the model's mean incidence is over many runs of the model. It's a little bit different across different runs of the model, but generally it's right in that range. We can look at dominant frequencies. Some of you will be familiar with Fourier transform. We can find dominant frequencies. We can look at autocorrelation function, as I did there. We can look at histograms of values at sample points of time, or cumulative distributions like this one, right? Giving year to year in observed data, how big were these? What was the cumulative distribution function if we looked on a yearly basis compared to what comes out of the model, over time, in terms of, the size of things. I will note the autocorrelation gets into this issue of kind of how far apart are these peaks, like how much is a peak now? To what degree is it likely to be followed by a peak, or is it separated from other peaks? The autocorrelation function can pack a lot of information in about that. Network structure, we have data from the world, from some sort of network-related data. We could potentially compare it with summary measures from the model. If we have spatial locations, and some of our models, we've done spatial movements of people and compared that against comparable data we have from the world for mobility, radius of gyration. These are all, different types of measures that, again, avoid point matching. The goal here, again, is, look, how do we have a model that we test how well it explains this, right? Josh Epstein, formerly at Hopkins, now at NYU, I think. Maybe he's at CUNY. I think it's NYU. He has commented, look, you don't really understand a phenomenon in the world unless you can generate it from a dynamic model without presupposing it. That's how we understand something. If we can build a mechanistic model, a model that characterizes how that is generated from some underlying substrate without presupposing it, without hardwiring that in, we show how it emerges from it, right? And that's what we're trying to do here. We're trying to show how this emerges. We're trying to see to what degree our model does our model account for those emergent patterns? And here are some measures that we can use to account for this without going after the fool's errand, without pursuing that, tilting at windmills and trying to match each and every peak here, which is a poor measure of model performance. It is the wrong measure. It is too fine-grained stochastically a measure, and it is unrealistic as measuring the effectiveness of a hydrological model by how well it predicts the exact time of waves lapping at the university bridge. We can specify discrepancy functions. If you look at this that paper, we had a weighted discrepancy function here. We made use of some that were sort of motivated by sort of an approximate Bayesian reasoning. We had a likelihood function reason about a normal value of a normal PDF probability distribution function with a certain sigma and a certain mean, and asking about the negative log of these and having weighted values for each of these adding up. So weight, the autocorrelation match, how far off the models, the autocorrelation function for a given time is as generated by the model versus corresponding one from the empirical data. And then for that cumulative distribution function, and then for the mean, we're just looking here at cumulative distribution function for the mean autocorrelation, and then there's, the age specific one, etc. I would note that the supplemental material here provides more detail. Okay, well, we're running out of time here. Perhaps I will leave my comments here on similarities between calibration and regression, particularly nonlinear regression, till tomorrow, till the lab session. I'll also tomorrow be looking at actual global optimization algorithms and comment on this process of trying to take this cumulative this discrepancy function, this measure of how well the model matches different empirical data, and trying to make it as tight a fit as possible. We will see that we can use optimization algorithms to do that, to savvily find assumptions about parameters that makes that match as effective, as close as possible. And so tomorrow we'll go through this with some matches, and we will explore some of the options and some of the considerations. I will just note one factor that I am brushing under the rug at the moment. I will talk about it tomorrow. And I'm a little bit shocked that I don't have a slide right away. I will simply note, I don't understand why I'm not finding the requisite slide. I will simply note here that ABMs, because they exhibit significant statistics, have been emphasizing not doing point matching. But also, we have to recognize that a given run of a stochastic model might not be, it's not in general going to be representative of all outcomes, right? Like each time we run it, we may get somewhat different outcomes, sometimes significantly different outcomes. So in general, when we calibrate an ABM, We seek to find the best set of parameters, the assumptions about less well-known parameters, the parameter vector for those less well-known parameters that leads the model to best match the observed data from the world. We have to recognize that if we only run the model once to assess that, we may deal with the fluke. We may see model outcomes that are quite different from what we would run it with the same parameter values, what we would get with the same parameter values if we ran it again, and if we ran it again, and if we ran it again. So commonly we will rerun it with many so-called realizations or replications, as any logic's term, again and again and again, trying to find parameter values that on average yield the best fit. And that's what's going on here. That's why the model results exhibit these error bar or these box plots, because some model results yield small values here, some yield higher values. And if you only ran the model once, it would sample from each of these, right? It would sample from each of these. It would sample from each of these. If you ran it again, it might sample somewhat differently. And as you could see from the whiskers on either side, like sometimes you might get something up here and you say, oh, that's a very poor fit. Or sometimes you might get one down here and you say, that's amazing fit. But no, that's not reliable. You want to do it again and again and again and get a fit that on balance is a pretty darn good match against that empirical data, even though we only observe one realization from the world, right? We don't generally have the luxury of observing the world playing out many times in different ways. So tomorrow, from this chair, I will lead a session where we'll examine some hands-on calibration, and we'll observe some of these issues in practice in trying to match data. So that's tomorrow. I will return to my office as I am wont and reconnect in 5 or 10 minutes in case anyone would like to rejoin, and look forward to a productive office hours now. Take care of that. We'll see many of you tomorrow. Take care.